All right, let's get started. I hope everything's going well for you. The topic that we're going to start today is what I consider to be essentially the heart of the course. So we've done a lot of stuff talking about probability distributions and we spent some time recently applying this method of maximum likelihood. And what we're going to do now is we're going to bring it all together and we're going to answer the question, if I want to put a straight line through a linear set of data, what is the best choice for the slope and intercept? And we're going to do better than, what's interesting about this question is you've probably been drawing lines through data since sometime in high school. And so the first way you do it is you draw your data, you draw your plot, you have your data points that are kind of linear. And then you just take a ruler, you kind of line them up, and then you draw a straight line, through the center of those points, and then you calculate rise over run and stuff like that. So you've been doing that kind of stuff for a long time. Today is the day that we're going to find out what's the proper way of finding the slope and intercept. Okay, before we get into all that, let's just remind ourselves of what we were doing. We use this method of least squares to determine this weighted mean and the uncertainty in the weighted mean. So that was the case where we had n measurements of some quantity, and each of the uncertainties in each of those measurements is, in general, different. And the weighted mean came out to be like this. It has the property that points that have small values of sigma are more important to the mean than those that have a large uncertainty. We confirmed that if you considered the special case where all of the sigma i's were identical and equal to just some constant sigma, then the sum that shows up here in both the weighted mean and its uncertainty reduces to just n divided by sigma squared. And if you make that substitution in here, and then this top sum would be 1 over sigma squared times the sum of xi, then our mean and uncertainty reduce to the familiar values for like just a regular mean, and this is the weighted error. Okay, so today it's going to be a so-called least squares fit to a straight line. We'll see what this term least squares is referring to in a few minutes. Okay, so the motivation is that we will often measure a quantity y as a function of x. So, when we were talking about calculating means and stuff like that, it's the picture we had in mind is that we just measure the same value of x over and over and over again. But that's often not what we would do. Like the simplest possible example you might imagine is you could measure the current in a wire as a function of the voltage you apply across it. And so you don't measure the same current 10 times for the same voltage. You measure the current once for voltage V1, then you change the voltage, you measure a new current, and you can plot that data. It's a straight line. The slope would be related to the resistance. So we haven't figured out yet how to formally analyze that type of data, although we do it all the time in the lab. We just blindly rely on something like Python to do the fitting for us. So instead, repeated measurements of a value x, we make a series of measurements of pairs of values xi, yi. Okay, and usually x is the quantity that we're controlling, and we're measuring the response of y. So for example, the example of applying a voltage across a wire and measuring the current, maybe we control the voltage just using some knob on our power supply, and then we measure the response to current using some ammeter or something like that. Okay. Because we're controlling X, usually the uncertainty in the X values are negligible, because that's something, if we're controlling it, hopefully we've designed our experiment where we have fine control over that. We can set the value of X precisely compared to the precision with which we measure the response Y. All right. Whoops. For example, let's consider linear functions. So one of the things from the lab, if you do Boltzmann's constant measurement, you would measure the ln of a current in the collector of your transistor, and that would be equal to this function, where we set the voltage across the base emitter. So we set the base emitter voltage, we control this V, and we measure the response of the current. And it turns out the ln of I is a linear function of the voltage. So if we set Y equal to ln I, it depends linearly on the voltage. So this linear function would be something like Y is A plus BX, where this is the intercept and B is the slope. So in our example, A, the intercept would be ln of I naught, and B, the slope, would be E over KBT. And so this is the slope. All right, and so in that particular experiment, we assume that we know the electron charge, and we measure the temperature, and so the slope allows us to find out the value of Boltzmann's constant Kb. So what you might do is you might generate a plot of Y versus X, and then you have some data points in here. Maybe some have big error bars and some have little error bars for some reason. And the question is, what is the best line to put through this data? Okay, so this one would have kind of a shallow slope maybe. And so you'd have your intercept A here, and then this would have a slope B that's equal to rise over run. Okay, so given a set of data, say xi, yi plus or minus sigma I, what are the most probable values of A and B? Okay, again, just like we were talking about with when we were trying to find how to calculate means and stuff like that, what we said is, like, all we can do is we can come up with some sample distribution of data that's sampled from the parents. The parent distribution has the true mean. All we can do is make our best estimate of what we think the true mean is. Same thing's going to happen here. We only take some small subset of data, a sample distribution of data, and we're going to try to say, based on the measurements we've done, what are the best estimates of A and B that we can make? Okay, we'll never know the exact true values. All we can do is take our data set and see if we can figure out what are the most probable values, best estimates. So in our approach, we will assume that the uncertainty in xi values are negligible, compared to the uncertainty in the yi measurements. Okay, so that's just another way of saying that we're gonna neglect the uncertainty in the x values and consider only uncertainty in y values. And again, that's just because we're controlling x and we ought to have fairly good control over it. Okay, so we will examine the deviations between the measured yi value. So for example, in this plot, each of these points has a particular value of y. So if this, I'll just pick one of them. It doesn't matter which one I pick. So I pick the ith point and I go over here and I say, all right, here is the value yi is sitting right there. And then what we're going to do is we're going to compare it to the corresponding value of y from our straight line. And so if this occurs at x equals xi, then this green point on the red line corresponds to y evaluated at xi. So what we're going to do is we're going to look at that deviation for each one of our n measurements, and we're going to try to do something where we minimize that net deviation. Okay, so we could, for example, add all the deviations from every single point and then just adjust the slope and intercept until the sum of those deviations go to 0. Or they won't go to 0, maybe they go to some minimum value. Okay, so that's sort of what we're aiming to do. There will be some wrinkles that we'll get to in just a second. Okay, so we're going to look for the deviations between the measured yi and y calculated from xi. And so that would be delta yi is going to be the y value of the ith measurement minus y evaluated at xi, where this is going to be calculated from the equation of that red line. And so what it'll be is yi minus the intercept plus the slope times xi. Okay, good. So we expect delta yi to be small for good choices of A and B values. So what I'm going to argue is that this metric, delta yi on its own, is not going to be a very good choice for figuring out the best fit value, right? Because I could imagine the following scenario. Here is some set of XY data. And so maybe we'll have some data scattered about like this. And I could draw a line through them that does something like this. Okay, and so if I was to pick a point here and I would say delta yi is going to be yi minus, so yi minus this will be a negative contribution. So this would be negative. And over here, if I pick one, here, let me put another point in here, something like this. Then we would have this delta yi would be positive, because the measured point is above the point calculated on this line. So then if we were to do the sum of all of the delta yi's, it would average out to a small value because all of these positive ones would compensate with these negative values. And so that's not really a good metric because I can have what's obviously a poor fit that does a decent job of making the sum of these deviations small. And so that's not what we're looking for. Okay. So delta yi on its own is not a good measure of a quality of fit. In the example above, the sum of delta yi would be small, even though the fit is obviously poor. So we're going to stick with this idea of working with these deviations, but we're going to make a little revision. We're going to think more carefully about this. Okay, so let's just go over here. We'll start a new fresh page, a better approach. So what we'll do is we're going to assume that the yi measurements are drawn from a Gaussian distribution or a normal distribution. So, I mean, the reason we spent so much time on distributions at the start of term is so that we could make use of some of their properties here, especially of the Gaussian distributions. Okay. So what I mean by this is, let's imagine that we had this X versus Y plot. And maybe what we're going to do is we're going to sit here at xi, and we're just going to make a measurement of yi, and maybe it sits over here. Okay, and so I'll say that this is measurement yi, like number 1. And then I'm just going to sit here at xi, and I'm going to make another measurement of yi, and I'll get a different value this time. And so we'll get a yi2, and then I make another measurement, and I get yi3, sits over here. And we just keep doing this over and over again. And if we did that type of measurement, what we would end up with is like a little cluster of points. And there will be like a big high density of points in the middle, and then there will be few points out at the extremes. And if you do that, we could make like a little plot of the density of points as a function of y. And if you did that, it would look something like this. Here, let's see. I want my peak to be where the points are the densest. So that's going to look something like this. And over here would be the average of yi. And we would have some width to these points, sigma I. So in practice, we don't do this. We're going to sit at x once, this xi value once, and make one measurement. But we're just going to think that, like, if we did repeat the measurement over and over again, I would get some average value, and I would get some sigma, some standard deviation. Okay. So our Gaussian distribution of yi values would have a mean of, say, y0 at xi is going to be some a0 plus b0 xi, where a0 and b0 are the true parameters that describe our line. And those true parameters are unknown, and we'll never know them exactly. We'll just make some estimates of what we think they are. Okay. The distribution also has a standard deviation, sigma I. Okay, good. Well, that's nice because we know some things about Gaussian distributions and calculating their probabilities, and we know some things about calculating values using this method of maximum likelihood. So we could say the probability of measuring a value of y between, let's say, yi and yi plus delta y is, okay, well, there's nothing new here. We've done this a whole bunch of times. We were just writing them in terms of x, but now we're just going to write them in terms of y, but everything's exactly the same. There's the Gaussian distribution in the denominator has a 1 over root 2 pi times sigma I. Delta y is the width of the interval that we're thinking about. And then there's an exponential of, let's see, minus 1/2 of yi minus y0 xi, right? So this before was like x minus the mean. We replace our x with y now, and then our mean comes from that expression up here, the a0 plus b0 times xi. We don't know those values of a and b, a0 and b0. We're going to try to find them. Okay, and then we divide by sigma I. This whole thing is squared. I need another bracket in here. Let's see. Oh, give me the 2. Okay, this is all squared, and then we got to close our brace. Okay, and now everything we're going to do from here is pretty similar to things that we've been doing for the past couple of classes. We're going to say, all right, that's the probability of getting yi at xi, but what's the probability of getting the whole data set, like y1 at x1, y2 at x2, y3 at x3, and so on? Well, it's just the product of all of these things. So the probability of making a set of measurements x1 plus or minus x1 and y1 plus or minus sigma 1, x2 and y2 plus or minus sigma 2, and so on to xn, yn plus or minus sigma n is. Okay, so P. This probability is going to be a function of A0 and B0. Before we wrote these as a function of mu, mu was what we were looking for. This time we're going to look for these two parameters, the slope and intercept. Okay, so it's just going to be the product of all these individual probabilities, which is going to be, let's see, we'll get the product of I equals 1 to n of, let's see, we'll have our delta y's in there, we'll have our sigma i's and root 2 pi. Just like before, we're not going to care about this because we're going to do it. We're going to try to maximize these probabilities by adjusting A0 and B0, and this coefficient doesn't involve those. So I really don't care about the coefficient, but there it is anyways. And then we have a product of exponentials, which we could write as an exponential of a sum. And I'm probably going to run out of room again. Okay, good. Oops. So we have our minus 1/2, and then sum of I equals 1 to n. And now we're going to have our, let's see, yi minus y0 at xi divided by sigma I. And then we got to square all that stuff. And like so. Okay, good. So to find the best estimates of A0 and B0 from the measured data, we will maximize P of A0, B0 by minimizing the stuff that's inside the exponential without the negative sign. Now, the stuff in the exponential now is given a special name. So we're going to call chi-squared. In fact, we're going to minimize everything except the 1/2 factor and the negative sign. So I'll forget about the 1/2 as well. It's just an overall constant. It doesn't matter. So we're going to define chi-squared to be the sum of I equals 1 to n of our y measurements minus the y values calculated from the xi values in our measurements, divided by sigma I and squared. And so this thing is called chi-squared. Chi is just the name of the Greek character. And it is a goodness of fit parameter. You can see now why this is called a minimization of a least squares method, because we still have our deviation, but now what we do is we square it before we do the sum. What our first approach, our simple-minded approach, was just to minimize this thing. But we said, well, we could have large deviations, half of them positive, half of them negative, and we still get a small value for the sum. So once we put the square in, these deviations, whether the difference comes out to be negative or positive, doesn't matter, because we're going to square it before we do the sum. So we're always adding positive values. So if we minimize that, that is a good parameter to test the goodness of fit. The other benefit this has is that it's weighted by 1 over sigma squared. So points that have very large values of uncertainty are going to be less important because we're dividing by a large number to terms that have a small value of sigma, where we divide by a small number and make a larger contribution to the sum. Okay, good. So for our linear fits, this chi-squared is then I equals 1 to n sum of yi minus a minus b xi over sigma I squared. And so this is the thing that we want to minimize. Okay. Now, how are we doing here? Oh, still more than 20 minutes. That's good. Okay. Last week, the example was a little simpler because we just had an x minus mu, and we did our minimization with respect to mu. Now I have two parameters that are unknown, a and b. How do you minimize with respect to a function of two variables?
You're gonna take a partial derivative?
Partial derivative with what?
Oh, like a mixed partial derivative?
Yeah, I think almost. I think you're on the right track. Okay, so to minimize, whoops. No, what we're going to do is we're going to individually minimize with respect to A, and then we'll do another minimization with respect to B, And then we'll end up with a system of two equations that will allow us to solve for two unknowns. So each equation will involve both A and B, so they're going to be mixed, but we should be able to solve that system. It'll be, you know, let's say marginally complicated, but I think we'll get through it. We'll probably get through it. Let's see. So minimizing chi-squared with respect to A and B. Okay, so we'll have to do a d chi-squared dA and set that equal to 0. Okay, so what do I get? If I do the A derivative, every time I take the derivative, I'll get a factor of 2 that comes out. So we'll get a 2, and then we're going to get the sum of, let's see, I equals 1 to n, and then we'll have a yi minus a minus bxi over sigma i. The square is gone. And then what else am I going to get? I'm missing one thing. What am I missing? A negative 1 over sigma. So we'll get a negative sign, and we'll get another factor of sigma, and so we get the squared. Okay. All right. So that's that. And then we have to do a d chi-squared with respect to b equals 0. Some of the stuff is going to be the same. So this time, let's see, what do I want to do? I'll put my yi minus a minus b xi here. When I do the derivative with b, I'll still pick up a minus sign. So I'll put the minus sign over here. Now, yeah, it's xi over sigma I. So we'll get an additional factor of xi, and then we have a sigma I squared. Okay, good. So those are our two equations. So this is two equations and two unknowns, A and B. So in principle, we should be able to solve for these two unknowns. And we could do it just, we just do a bunch of algebra and solve it. I think we're going to take a more kind of structured approach to this. Okay, first, what we'll do is let's break this into individual terms. Both equations have 1, 2, 3 terms. So 1, 2, 3 terms. So we could write the sum of 3 terms as 3 sums. So we'll start with the derivative with respect to A. I don't care about the minus 2, right? I could just divide by minus 2. I have 0 on the left, so I could just get rid of the minus 2. Okay, so my first term is a sum of yi over sigma I squared. So we have a sum of yi over sigma I squared. I'm not going to draw all the I equals 1 to n. For all of the sums that we're going to do right now, all the sums are from I equals 1 to n. So I'm just going to omit those. Okay. Then we get a minus a over sigma I squared. I'm going to take that to the other side of the equation to get rid of the minus sign. So we have a is a constant. I'm going to take it outside the sum. And then we have 1 over sigma I squared. B is a constant. I'll take it outside the sum. I'll get rid of the minus sign by going to the other side. And then we'll have a sum of x over sigma I squared. So we should get a plus b sum of xi over sigma I squared. Okay, good, and that's what I have. And for the second equation, we'll get similar stuff, but we're gonna have like an extra xi factor floating around. So we'll get xi sigma I over sigma I squared equals a, and then it's xi over sigma I squared. And then it's a b xi squared over sigma I squared. Okay, so what we're going to try to do is solve this system of two equations for the two unknowns, A and B. So what I claim is that we could represent everything here in these two equations as a matrix. So this is of the form. Okay, so the claim is that this is of the form UV is equal to UA, UB, VA, VB, KB. Okay, so we just have to identify which factor here corresponds to these. The A and the B are obvious. Like this A just represents that A, and this A, this B represents this B and this B. Okay, so if we were to identify this thing as U and this as V, then we could say this is going to be UA and this will be UB. Right, UA is the factor that comes from the A derivative and has the A coefficient. UB comes from the A derivative and has the B coefficient. And so likewise, we'll say this is going to be VA and this will be VB. Let's just do this matrix multiplication and show that it's going to have the structure written above, right? So matrix multiplication, we have to take UA times A. So it's going to be A, UA, and then plus UB times B. So plus B, UB, and so that's going to be UV. And then over here, we have VA times A. So it's A, VA, plus VB times B. So this is B, VB. And if you look at this equation, U is equal to AUB plus BUB. This is U is AUA plus BUB, and the second equation is just this bottom line. Okay, so this seems to work. They correspond to one another if we label them like so. All right.
After that first entry in the matrix be
AUA, yes, you are correct. Yes. Thank you. Good. Okay. So if we have, I'm just going to write down our matrix equation again. So if this is true, then, what we want is these unknowns. I can just multiply by the inverse of the square matrix to isolate AB. So then AB must be equal to, if I call this matrix A, it must be equal to the inverse, A inverse times UV. Does anyone know what's the, yeah, go ahead.
How do we know that that's an invertible matrix?
So how do you know if your matrix is invertible? Yeah, so we would have to evaluate the determinant. So let's do for a 2x2 matrix, A inverse is equal to 1 over the determinant of A. Does anyone remember how to get the inverse of the 2x2 matrix?
1 over the determinant.
So yeah, VB, and then it's minus UB, and then it's minus VA and UA. Just full disclosure, I don't remember this. That's not something that's in my head. But you probably have done matrix algebra more recently than I have. Okay, anyway, so there it is. So what we require, you can't have this determinant equal to 0, otherwise it blows up, right? That's the problem. So as long as the determinant is non-zero, this thing should be invertible. Okay, so therefore, it must be that this AB is equal to 1 over the determinant of A times this so VB minus UB minus VA UA UB. Okay, and then we have all these things, right? And we could calculate the determinant. The determinant of A is equal to, what would it be? You would take the diagonal in one way and subtract it from the diagonal in the other way, right? So it must be, yeah, UAVB minus VAUB. That's right. So you take UA times VB and then minus the other diagonal UB and VA. Good. So let's see, we could just do this matrix multiplication and solve for A. So A must be equal to what? VB times U. So it's, how do I want to write it? Yeah, VB times U minus UB times V. Minus UB times V. And then we have to divide by the determinant UAVB minus VAUB. And likewise, B would be equal to minus VA times U minus VA times U plus UA times V. So UA times V, and then we have to divide by the same determinant. UAVB minus VAUB. Okay. There they are. What we're going to do if we have time, yes, is we're going to write down these things in terms of how we defined all these U's and V's. Okay, so let's just go back up here. We have all these definitions for the U's and V's. I won't scroll up and down constantly to look them up. I'm just going to write down what our solution for A and B are in terms of these sums. Okay, so subbing in for our definitions of U, V, UA, VA, UB, VB, we get, okay, we'll start with A. So it's going to be the sum of xi squared over sigma I squared. You could double check this, okay? That's an exercise for the student. Double check that I haven't screwed this up in some way. Okay, and so this term is actually the second one in, sorry. No, it's the first one. The A has a positive for the first one, and then it's minus something. And that minus something is going to be the xi over sigma I squared and xi yi over sigma I squared. And then we have to divide by this determinant. So it's 1 over sigma I squared, xi squared, sigma I squared minus. And then we'll scroll back and let's look at one of them. The VAUB. VAUB. VA is xi over sigma I squared. And UB is xi over sigma I squared. So VA and UB are actually exactly the same. So in this determinant, when you have a VAUB, this is the product of the same two sums. And we could write that as the sum of xi over sigma I squared, all squared. Okay. So This is usually written as whoops. This is usually written in the following way. A is equal to 1 over delta of the numerator. So delta is going to be defined to be everything in the denominator. So we get xi squared over sigma I squared, yi over sigma I squared, and then it's minus xi over sigma I squared, and then it's xi yi over sigma I squared. Okay, so that's A, where delta is just the denominator. So it's 1 over sigma I squared, xi over sigma I squared minus the sum of xi over sigma I squared, all squared. So that is your intercept. Notice that everything in here is known because we've made measurements of xi plus or minus y, xi and yi plus or minus sigma I. And so we have every single value in here. You just have to evaluate all of those sums and out pops your intercept. So that's what something like Python or MATLAB or whatever tool you're using to do linear fits, it should be doing this calculation. And so there's no guesswork in determining the intercept or the slope. They are exactly determined from your set of measurements, and there's no freedom for adjustment. Okay, so in the same way, oh, perfect. In the same way, if you do this for the slope, you will find that B is equal to, it has the 1 over delta. So that's 1 over the determinant of that matrix A. And then it's the sum of 1 over sigma I squared times xi yi over sigma I squared minus xi sigma I squared times yi sigma I squared. And that is the slope. So these are the best fit parameters for a weighted linear fit. What we haven't done is we haven't figured out the uncertainties in our estimates of the slope and intercept. Who can think of how are we going to do it? How do we do all of our uncertainty calculations? We are going to do propagation of errors. That's exactly what we're going to do. And we're going to find that our friend, the Kronecker delta function, will be very helpful. Okay, because we are going to have to take partial derivatives of A and B with respect to, say, yj, the jth measurement of y. And so we'll end up doing derivatives of like dyi with respect to dyi dyj. And that's going to be a delta ij. That delta function is going to be very useful because, remember, it's a killer of sums. And so it'll clean up these expressions quite a bit. The other thing to notice is that this delta doesn't involve the y's at all. So when we do our propagation of errors and we take these derivatives with respect to yj, this delta is just going to be a constant. So we won't have to take derivatives of the delta thing. It's only the stuff that involves the yi measurements. Okay, so next time we use propagation of errors.
That can you give us like the covariance meters in Python?
Yeah, in fact, we will see where that covariance matrix comes from. Yes, yes, we will see that. So next time, use propagation of errors to find sigma A and sigma B. Yeah, so that covariance matrix that you see in Python, we often will find the uncertainties of the best fit parameters from the diagonal elements of that matrix. We will see that eventually. Yeah. Okay, good. So then that's it for today. So we'll pick this up on Friday and we'll do our uncertainty analysis on Friday. All right, thanks very much.